So, all right. I guess we'll start. Is there any questions before I get started, or anything you want me to focus on or look at? All righty. So I'm just going to go over the packet from last year. I'm not sure if this is available, but if it, I'll drop it in the chat uh, so you can have it. Let's see. Uh, Shoot, I don't have it downloaded. I'll drop it in the chat afterwards. But basically, just wanted to go through this so you can have a idea of what the competition will be like. Are you guys doing it in person or online or in a team, or not sure yet? Okay, uh, that's good. Or uh, sorry, I don't know how to say your name. Jawan, are you doing the competition? Okay. Well, I'll just go over it anyways. Just uh, it could be useful to you as well. So the questions are ranging from easy to hard, with harder problems being more points, but a lot more complex. So uh, it'll be kind of a balancing act. So depending on how you are going through this, like if you have a team, then you might need to come up with like some strategies on how to split up the problems or work together to tackle some of the harder problems. But there's all of these like the frequently asked questions that are on the CodeQuest site. Uh, Pretty common stuff that you've seen if you've been using the website, and some rounding tips and trigonometry equations, and then the ASCII table, and then some of the terminology that they use. So I'll paste the link before I go, and then you can kind of get a feel for what this is going to be like. And so this is the first problem in the packet from last year. And so it's pretty simple, but you'll notice that there's a lot of like extra wording. So I think I would recommend like skimming the problem background to get a understanding of what the question is, and then read the problem description, because that's where the main meat of the problem is. So like for this one, there's all this background about cryptography, but basically this problem just wants you to parse a string and follow some cipher rules to decipher the input string. So not too bad. Once you know the rules, then you can easily write something up to iterate through the string and generate the output. But the questions do get a lot more complex. Like I think this one, not too bad. I think, oh, this one, like there's this maze problem where, and stop me if you want me to, if you want to talk about any of these, but this problem is essentially you have to read in I'll show you the sample input. You're basically gonna have to read in this formatted maze where these dashes and pluses are walls, and depending on where on the edge of the wall these V's are, will indicate if it's your starting or your ending point. So for this one, it would be this is the starting point and this is the ending point. And you want to find the shortest path through the maze. So this is much more involved than the first one, because you first have to read in this maze into some sort of matrix, and then write up the algorithm to find the shortest path, which if you remember, I guess now a few classes ago, maybe a month or so ago, we went over or briefly went over depth first search and breadth first search. So in this case, you would do something like a breadth first search because that would give you the shortest path between your starting point and your end point. And yeah, if you want me to talk more about that, we can. But essentially, so this question is 90 points or 100 points, and it's kind of near the end. So it would be good to look through this packet if you're doing the competition to just get an idea of how difficult the problems are so that when you go into it, you can just sort of look for, say, like a 50-point problem that you think you feel comfortable with, or if you're in a team, breaking up this problem into, say, one person reads in the input and will output the maze in a certain format, say like in a certain data structure, like a matrix where a 1 is a wall and a 0 is a empty space, and you provide the starting and ending indices, and then the second person can go and write the breadth first search, and then you come together. So that could be one way to break stuff down, but pretty good variety of problems. Another thing I would recommend is, since a lot of these do follow the format of how they pass in the inputs, just having something from your previous like code quest problems that you've done, like to parse the inputs so that you don't have to start from scratch every single time, especially like the first question where it's like, oh, just parse a string. If you have something that is already just parsing a string, then you could just modify it to the question. And yeah, so like this would be a good problem to do because I feel like there's a lot of maze problems, and they try to like change it a bit so it's not so easy for you to just Google. And that's another thing. I think Googling is allowed, but not Chat GPT, even though I don't think there's a way they can stop you from using it, but I would just recommend not using it, so that this is really more a test of your skills as kind of like a checkpoint to see how well you are coming along. But it's not really, the main thing isn't about winning the competition. It's about trying to see how well you can solve these problems in a somewhat time crunch scenario. So yeah, is there any questions? If you want, we can go through some of these or try. I'm not even gonna attempt, my Java is not good enough to do live, but I could definitely try and walk through some of these algorithms if that would be useful, or whatever would be good. I'm open to anything. Or if you want to talk about other topics, like whatever, like GitHub or general software engineering, just let me know. We could talk about anything. Cool. This problem? Sure. All right. Let's read the problem. Okay, the background is really not too relevant, but all right. You will be provided with some rectangular mazes and will have to write a program to read the maze diagram, then determine the shortest path through the maze and report how many cells were traversed to move from entrance to exit. Moves are only made horizontally and vertically, and of course may not be made through the walls. Each cell within the maze is represented by a 3x4 rectangle or horizontal rectangle of characters, bounded on each corner by a plus sign, and each cell shares its edges with its neighbors. And yeah, so this is unfortunately, this is not too simple, or I guess it is simple, but it's like kind of a pain because reading it in, you have to read line by line, but a single line isn't uh, a correspond to a cell. So let me pull up, or let me switch what I'm sharing. Uh, I guess let me finish going through this problem. But yeah, so I'll break this down into the two components we were talking about before. One, like, or I guess three. So you'd have your main function, and then one function would be to read in the input, and then another function to, given a matrix, find the shortest path. So reading in of the input is a pain, but shouldn't be too bad. You just have to basically loop over all of your, and they give you the height and width, so that helps you set the bounds of your for loops. But basically have to abide by the rules. Let's see here, like, and again, it's a little, to me, a little silly that they do this, but it's just so that it's not easy for you to like Google it and find the answer. So when they pass in the input like this, it makes it a little harder to just Google. But I will go over the breadth first search part of this. Now let me share this other screen. Okay, hopefully you can see the text editor. Try to zoom in a bit. It would let me. All right, well, hopefully that's not too small. Or zoom. All right. So BFS, the stands for breadth first search. And so since we want to find the shortest path from an index, our start, which would be some index I comma j, to an end index, say like k comma z. Breadth first search works pretty well because the algorithm basically works like this. We start at some index, say just for this example, 0, 0. And then we generate the neighbors of that index. So basically, in this case, since you can only move up, down, left, and right, you'll generate up, down, left, and right. So that would be, was that a 0, 1, 1, 0, and then -1, 0. Oops. 0, 1. That's the right, or up 1. Then we go to the right one. Then we go to down, or to the left one, and then 0, -1. So you basically generate the 4 neighbors that would be around that given index. And then you need to verify if those neighbors are valid. So basically within the bounds of your what's this thing called again? Your maze. So basically for each index, the indices have to be greater than 0 and less than height / width for either the X or the Y component. And so once you have the valid neighbors, you're gonna push, or I guess the terminology is a little different, but basically add valid neighbors to a queue. So this is how breadth first search differs from depth first search. So essentially you are adding the neighbors onto a queue, and then the next step would be, while depth first search would use a stack. So the next step would be to pop queue, and then you would like repeat. And then I guess basically start at some index. But basically, since this is a search algorithm, where the first thing you do is when you're at some next node, you want to check if this is the end. If so, you return. And so this, well, it's not looping around this start, but this is just like kind of a note. But essentially the main part of the loop is, for each node you're at, you basically, or I guess let me start again. So this start at some index 00, so you can initialize your queue to start at the start index. So in this case, it would be, your queue would be 00. And then, so let's write that there. Add start index queue. All right, and then what we'll do is pop or take the, I think it's pop, or is, oh no, it's deck. That's just the term for DQ deck our queue. We get node. And so we're basically going to get the first node, check if this is the end. If so, return. Otherwise, we generate the neighbors, validate that, or verify that the neighbors are valid, and then we add the valid neighbors to the queue. And then when we do the deck again, we'll basically get the next neighbor or next valid index that we need to explore in the maze. So let me copy over the maze so I can just kind of show what that would look like visually. Oh, of course. Let me share the other screen. I can't share my, it doesn't let me share the whole, or my screen, so I gotta stick with this for now. All right, new share. All right, back to this. Okay, so for the breadth first search, the way this would work is we would start at this index, which depends on how you use the walls, but I would basically say this wall would be, see, it's a little confusing because they say each cell is a 3x4 horizontal rectangle. So is that 1, 2, 3, but like these dashes, oh wait, no. So this is a 4 and then 3 down. Okay, so yeah, so technically your starting cell would be this one. This top left one. And so basically you would start here, whatever the index, if you want to specify the top left is 00. And then you add all the valid neighbors. And so it only has one valid neighbor. 0 or 1 0. And then you do the same thing. This is not the end. So you add the valid neighbors. Oh, and that's another key thing. Since you don't want an infinite loop, you need to make sure you don't have you need some sort of like hash map to map indices to if you visited them or not. Or so basically a set. So once you visit a certain index, you need to say, not only, so once you check, is this the end? If it's not the end, you have to add the current index to your set and say, probably call it visited, say that you visited this index. And so that when you're at a part of when you go to the next node or next cell in the maze, when you're trying to generate or verify whether to add the neighbors to your queue, you need to also verify that the index of the neighbor is not in your visited set. So that'll help you avoid going back and forth like this forever. So essentially when you're here, the only neighbors that should get added is here and here. And based on how you generate like the order in which you generate your neighbors, say you generate right, left, up, down, you'll go right first. And since this has no neighbors, next place you'd visit would be here. And so because of the queue aspect, like, I guess let's look at an interesting intersection. Like say we somehow end up here and we go right. So we would we end up going right, but say we're here and we have the neighbors up and we've already visited left. But since this is not depth first search, we're not going to continue along this path. We're going to check the neighbors of whatever's at the top of the queue. So if we ended up here, actually, we would probably end up checking this space first. So since it's kind of like gradually spreading out from where we start and checking like every possible location so that we eventually get here and then we find the shortest path, but we haven't been keeping track of what nodes we visited. So that is a little tricky, but we could add one more step. So let me go back to sharing the other screen. All right, let's get rid of this. So I think the two things we need are, I think the list of nodes. Let me pull it up. Oops, pull it up over here. And all right. So I think the two things we need to output are the number of cells traversed. Oh, that's all you need. You just need the number of cells traversed. So that is a little tricky because in this for loop, we would just find whether or not like true or false if we found the path from the start to the end. So in order to find a path or find the number of nodes or number of like cells we visit in order to get to the end, we're going to need to do some sort of bookkeeping. So can't think of the best way off the top of my head, but one way could be to use the recursive form of the depth first or the breadth first search. And essentially you make this its own function. And so you basically have a function to generate neighbors, verify the neighbors, and then in this main routine that gets called from your like main function, you would basically, instead of exploring the next node, you would just call this routine again. And so that when it returns one plus whatever uh, the recursive call you made returned. So back to uh, back to the example inputs. Oops. All right. So basically, if you get all the way here and you're like, oh, this is the end index I've been looking for, you'll return one. This, and then you'll get back up to here and you'll do one plus whatever got returned to you. So that'll be two, and it'll work its way back the path. So then you'll get 9. That is essentially how I would go about it. But the recursive and iterative versions of breadth first search are a little tricky. And so should definitely go through. I think all these questions are on CodeQuest, the CodeQuest site. So, but does that approach make sense, or does anybody have any different ideas? Because there's quite a few ways, I think, to come up with a solution. So this is just one way. Okay, if not, we can just try and continue to look at different problems. Here, how about I download this so that you can look through it yourselves and then see if there's any interesting problems that you guys want to look at. Downloads. Okay, it's loading. Should be pretty quick though. Cool. All right. Yeah, open that up. It's in the chat. Then you can let me know what questions look interesting to you. Personally, I like maze problems, and I think that would be a good problem if you're planning on doing the competition or just in general, because these types of algorithms come up all over the place and lots of different varieties. So that'd be worth doing. I haven't looked at too many of these. I'll just talk while you guys look, because I haven't really looked at all of these as well. But this one just looks like a lot of parsing and a lot of if statements. So it's not too interesting, just a lot of edge cases and just being careful. This one was a little weird. What is this? It is pretty cool though. They make these questions related to Lockheed in some way, which is kind of interesting because a lot of these algorithms are algorithmic questions you see but very plainly, but they make the questions kind of fun. So pretty cool. But let's see. So quickly sample. So a topographical map, like think of like maps of like uh it shows the topology where I think lines that are closer together are like show a smaller difference in altitude change, and lines that are like farther apart are like steeper. No, yeah, steeper, I think. But yeah, so it's basically a way to show 2D, or no, topographical. That might be different. Well, either way, if we're taking a cross section, it's going to be a 2D map. But now I'm curious what a topographical map is. Oh yeah, it is the ones with lines that are a bunch of lines, and lines that are close is there's a small difference in elevation change, but lines that are further apart, there's a bigger change. So, okay, what is the inputs? Is this one interesting? If not, we could skip it, but right. Okay, a lot of text parsing. Oh, classic shopping cart problems. Working at adding a new automated convenience store to allow employees to buy snacks and drinks throughout the day. Employees can select what they want. Website. To write a program to handle processing. Okay, so again, just more processing input and generating output based on that input. So a lot of this is more so reading and understanding the parameters of the problems. Tree. Okay, I think they said this is one of the harder ones. Must design a program that can find the optimal path for a given plink board. That is the path that is worth the greatest number of points, given the specific arrangement of point values and bucket values. Okay, I feel like this one you probably have to read more of the description, but again, just seeing something like this was kind of interesting. Tree problems, again, like these depth first search, but I guess you could store it would be a little tough to store this in a matrix. So you'd have to store this in a graph. So graphs where you basically have a class that represents a node, where a node is like has a value, and it has pointers to other nodes, such that say 4 would be a node with value 4 and pointers to instances of these nodes where they have value 3, and they also have pointers to their children. And so these are interesting problems because tree traversal is common, but actually I don't know what kind of, if this really would be a tree, because these middle points, I don't know how that would be represented. So oh yeah, and very interesting. I don't know if these, it looks like the middle point is also connected to both of these. So it's like a fully connected tree, which is not common. All right. You all find anything in the packet, or really anything? I could try and go over a hash algorithm. Oh, this seems interesting. How about let's try and come up with a pseudocode for this one. All right, your team is working with Lockheed Martin to implement a new automated security process for verifying documents. Your program will receive a string of text representing a document being downloaded from Lockheed Martin servers. It must calculate a hash of that data, then compare that hash against the one provided by a different server. If the hash matches, everything is fine. If not, you'll need to flag the error so LM employees know not to open that document and it's been tampered with. So this is actually something that a lot of the programs do, because, or not even just for tampering purposes, there's like a lot of cool things that happen like with data transfers, because there's a lot of improvements and there's a lot of cool mathematical things that are done in cryptography and error correcting codes that we can be confident, say when we send the message. Let me try draw real quick. All right, sorry, sharing is such a pain, but okay. So I use my mouse. So essentially, if we have some computer, or say like this is your phone, and you want to send a message, like send some data, like of some bytes, like you want to send, oh, this is rough, 0101 to some computer B, there is some probability that the bits received that are sent by A are not the same bits received by B. So say B receives 1101. And so there's a whole bunch of techniques around cryptography and error correcting codes for us to be able to even manipulate what we receive to verify and get the correct input that we should have been expecting. But so this is not a problem or like of receiving like really bad data, because I think it's a pretty mature field. But if you're interested in quantum computers or other types of hardware where the error correcting codes are not like there yet, it is something to worry about. Like I've worked on some quantum computers where it's like the bits, the output of a function should be a certain thing, but because of the noise in the computers, you would be receiving different bits. So just a kind of aside, but something I think is kind of interesting to talk about. But okay, back to the problem. Hashes. So they essentially want a hash, which is essentially a function that kind of like the hash maps we use, where you have key values where you'll pass in the string and it'll generate an output. And they want to run this hash on two different servers so that they know that the values are the same and that the data is valid, essentially. So you developed or LM has developed a new hash algorithm for this purpose. Note that this is actually a bad idea in reality. You should always use previously published and cryptographically secure hash algorithms when one is needed. Yeah, so I think there's like SHA, SHA, and all sorts of things, but it's kind of a back and forth between, I think, I forget which group is which, but they're in like uh hacking and like reverse engineering. There's red hat groups and the black hat groups, I think. And so where one group is trying to penetrate systems and the other group is trying to harden systems. So there's always a back and forth between these algorithms and trying to find loopholes. Let's see. So the algorithm, this is the algorithm. We convert the given text string to binary by replacing each character in the string with a binary equivalent. Okay, we had the table in the beginning. And then add additional 1 bits to the end of the binary string until the length is evenly divisible by 128. So, oh, that does remind me. One thing for the competition, and just in general, freshen up on your modular arithmetic, really just to know that the modular division is the output is the remainder of the division. So if you want to check if some length is divisible by 128, you just do say n modulo 128, and then if it equals 0, then that number n is divisible by 128. So if you had, say, some string, what is this, 1 2 3 4 5 6 7 long, then you did 7 modulo 128, or the other way. Wait, add additional 1 bits to the end of the binary string until the length is evenly divisible by 128. So, oh, the total string, not just individual character. So, yeah. So say if you had 128, it would be divisible by 128. But if not, what would the next one be? 256. So if you had somewhere in like 150 and it wasn't modulo 128, you'd have to add the number of ones to get to 256, because that would be the next number. Split the resulting binary into chunks of 32 bits each. Cool. Initialize, there's a lot of rules, but this makes sense in a realistic sort of way. So initialize variables A, B, C, and D to the 32-bit binary equivalents of the following numbers. Okay. For each chunk from step 3, calculate new values for A, B, C, and D as follows. M represents the chunk, N, or the current chunk, N represents the index of that chunk. So we're going to do a bunch of like logical operations with the string and these numbers, and then concatenate the final values and convert the results into a 32-character hexadecimal. So yeah, this is, again, just a bunch of steps, but pretty cool and pretty useful and actual practice, even though this is probably not something we would do. We would just see something off the shelf. But oh, and they give nice descriptions, because working with binary can get a bit confusing. So like this rule, a left rotation of x bits moves the x most significant bit to the end of the number. Oh, okay, that makes sense. Okay, they're nice. I think subtraction and I guess addition too gets a little weird because of depending on how you round. So I think that could be an issue with differing results. But yeah, that's essentially that one. All right. Are you guys are you there? Hopefully I'm not talking to myself. Okay, cool. Is it good? Do I just Should I just keep going through different ones? I think we have about 13 minutes, but if there's anything in particular, go ahead and let me know, but just not all at once. Ooh. Ooh, this is rocket science. Okay, for this one, I'll read the background. I guess we'll look at this one because who doesn't love rocket science? Okay, we're working together to develop a new system for deploying CubeSats, small satellites. Okay, this makes launching CubeSats easier. Okay, what is the real question? Okay, we're working with the UK, create a program to determine how much fuel must be loaded onto the SL for each mission. On board the vehicle allowed to move as though on a two-dimensional grid. Okay. On each mission, the vehicle will have up to 6 CubeSats, which must each be launched at a specific location on the grid, while the vehicle is at a complete stop relative to the grid. This ensures that each CubeSat is placed into the appropriate orbit for its mission. However, the vehicle must also launch each CubeSat at a specific time to ensure that the CubeSat's orbit won't interfere with that of another satellite. Well, this seems very relevant to kind of the work I do, but not in 2D, of course, and a lot of other factors. But all right, has 4 thrusters, each allowing it to accelerate along either the X or Y axis, so it could go up, down, left, right. Each thruster provides a constant acceleration, 1 meter per second squared, while it's being fired. Keep in mind that the vehicle is operating. I wonder if it can go in diagonals. For example, let's say this. Oh wait, I'd be just skipping stuff. Just find that. Ooh, so this is kind of along the lines of like controls too, because especially for like a computer science sense, I think of moving as like, oh, like in the maze problem, oh, you just go, you +1 to go to the right, like -1 to go to the left. But in reality, if you want to stop, you need to reverse your thrusters in order to reverse your velocity. So this one might be pretty interesting if people are more into like robotics and stuff like that. So let's see, we start at 0, 0, moving at 0 meters per second. Here are relative to the grid. In reality, orbital speeds are measured in kilometers per second. Yes, because when you're in space, you will have to be moving quite fast. Getting to the launch coordinates is easy. Short burst on both the positive X and positive Y thrusters will cause the vehicle to start moving in the right direction. Once it approaches the launch coordinates, burst on the negative thrusters of equal duration will cause it to stop on target. However, a short 0.1 second burst on each thruster wouldn't move the vehicle very quickly. There's no way it would arrive in time to be able to launch the CubeSat. All right, so what is the question? Okay, they have some nice position equations. Okay, they derive time. All right. Okay, okay, we're calculating how much fuel is needed. So again, I feel like some of these questions, like you just have to pick and choose your battles. Like for the sake of learning and fun, I would do this one like casually, but I probably wouldn't pick this one just because it seems like a lot of reading and it's not 75 points is still a lot of points, but actually, that shouldn't be too bad. You receive, okay, the number of tests, and each test will include a line containing information about the initial state of the launch vehicle. It includes the following values separated by spaces. A positive integer less than or equal to 6, S representing the number of CubeSats, an integer representing the starting X coordinate, starting Y coordinate, S lines containing information about the launch parameters for each CubeSat on board. And the launch. So basically we need to travel to each coordinate, deploy the CubeSat. But then it's not, you have to abide by the physics equations provided. So pretty cool, but for the competition might be a little tough. But all right. Anything else? If not, that's really all I got. Really just informal today to just go over any questions you all have, but seems like everybody's been doing pretty well. I've been monitoring the CodeQuest classroom and people have gotten quite a lot of questions done. So, and I haven't been getting any emails or anything. So are we good? Anybody need anything?